Alright, so today I just want to talk about a 2D vector kinematics problem for physics. This one is not that hard to do, but I'm just going to give you a walkthrough. And yes, the question is from ChatGPT because I just wanted an example fast and simple. So it says a hiker moves as follows: 60 meters north, 40 meters east, 45 of south, 50 meters west, 30 degrees north, and it wants us to draw a rough vector diagram showing all three displacements, find the resultant displacement's magnitude, and find the direction of the resultant displacement measured clockwise from north. But I don't know about this part. Okay, so first thing I'm gonna do, draw a rough vector diagram. So the first thing you gotta do with all of these problems is you have to draw a compass first. So you know so you have an idea of your direction. So let's make north positive, south negative, east positive, and west negative. So it says a hiker moves 60 meters north first. So what I'm gonna do is this first thing, I'm just gonna place a dot here. That's where the hiker starts. And then I'm gonna draw a line up. And this is not to scale. It doesn't have to be to scale because it's just a rough diagram. But there's my first segment, and we're gonna label that as displacement 1, and it's 60 meters. So this is north. This is going straight up, just north. And then from that point, we go 40 meters east, 45 south. So what that basically means is we look east, and then we droop towards south at a 45-degree angle. So I don't have a protractor, so I'm just gonna try and be as accurate as I can. So that's 90, and then, oh wait, no, look at east, and then the angle would be on the outside. 40 meters, so the line's gonna be a bit shorter, so I would say like about there. 45 right there. 40 meters, it's shorter than the 20 meters, I mean the 60 meters. And now we can label this the angle, be 45 degrees. And what I like to do is also draw some dotted lines here to kind of create this triangle. Just so later we can break these into x and y components. And this is displacement 2. And this line right here, which is the hypotenuse, is 40 meters. Okay, so now from that point we go 50 meters west, 30 degrees north. So 50 meters that way, but we're looking west and we go 30 degrees towards north. Okay, so looking west, 30 degrees north. Here we go. So 50 meters, so it's a little shorter than the 60. And then let's say that's 10, 20, 30. right there. West, 30 degrees north. And now we'll put an arrow here. Don't mind it interfering with our what we put here. Can label this. That's way smaller than 30, but it's not supposed to be like 100% accurate. That's 30 degrees. Again, break this kind of like a triangle. And now we can see we start from here, go to here. That's first displacement, second displacement end up here, and third displacement end here, which is our ending point. And our resultant line is gonna look something like connecting from the end to the start. And how we're gonna find that is we're gonna put our data of our directions and where the hiker moves into an X and Y table. So let me just show you what that looks like. You're gonna go down here and then create a small table. Okay, I don't know what that was. Create a small table, like so. Then you put X, Y, and all your displacements. So displacement 1, displacement 2. In this case, we have 3 displacements that we need to find the total displacement of. And then our resultant, which is just going to be all of these added up. So first displacement, 60 meters north. North is going up, so that is going to be in the y component, and north is positive, so it's going to be in y plus 60. Displacement 2, 40 meters east, 45 of south. This is where we're going to have to break it up into x and y components. So if you look at this triangle that we've created here, the hypotenuse is 40. The line that's touching the angle is the adjacent, and the line that's not touching the angle and is touching the hypotenuse is the opposite. So now put this into x and y components. This is x, and this is y. For this, we can use SOHCAHTOA, which is an easy way to remember sine, cosine, and tangents relations to the sides of a right angle triangle. First thing to find the adjacent, we can use cos because cos, we need the hypotenuse and the adjacent, and we have an angle, which means we can find the adjacent. And the way we can do that is what we're going to do is cos, because cos angle is equal to adjacent over hypotenuse. We're trying to solve for adjacent. So therefore, our x component would just be the hypotenuse times cos of the angle. So this would be cos, and the angle is 45, so 45. And then our hypotenuse is 40. So 40 times cos 45, what does that give us? That gives us about 28.284, and we're not going to round into the final step. And if you want to know if this is going to be negative or positive, just look at the direction it's heading in. It's heading in east direction, right? Because this is going east. So this in the x component here that we would just put plus 28.284. For the y, it's basically the same thing, but instead we use so we use sine. So it would be 40 for the hypotenuse, sine 45. And that gives us approximately the same thing, 28.284. And in this case, it's going down, so this is going to be a minus. So minus 28.284. Then for the third displacement, 50 meters west, 30 north. Okay, so this is our triangle. This is our adjacent. I know it's a little hard to visualize. That's the that's the opposite. Right, our hypotenuse. Oh, I forgot to write 50 meters, but our hypotenuse here is 50 meters. Okay, then we just do the same thing. Our adjacent in this case is our x component because it's going horizontally, and our opposite, which is this line, not this other yellow line that I drew, is our y component. Then we just do the same thing. So our angle here is 30, our hypotenuse is 50. So for x, the adjacent, we would use cos 50. Oh no, 50 cos 30. So 50 cos 30, that gives me about 43.3. And let's just do the other opposite real quick. So opposite, we'll use so sine theta equals opposite of our hypotenuse. So our opposite will be hypotenuse times sine the angle. Angle is 30. So we do 50 sine 30. That gives me perfectly 25. Now let's just determine if these are going to be positive or negative. So this is going west. The x is going west, so this is going to be a negative. So minus 43.30. And then our sine is actually going up. Let's see, it says north here. It's going up, so this is going to be plus 25. And then now to find our resultant, we just add all of these together. There's 0 here. So 0 plus 28.284 and then minus 43.30. So minus 15. Actually, I'll just put it under because I didn't give myself enough space. Our x for our resultant will be negative 15.016, and for our y, minus 2.284 plus 25, it will be positive 56.716. Now what you want to do with this is create your own triangle now. And then you solve for the hypotenuse, which is basically this long yellow line that I drew, not the opposite of our last displacement. So what I like to do first is first thing I'm gonna see is which one has has more value, and I'm gonna draw that one first. So I'm gonna go for my origin. Let's say, okay, this is our 56.716y, and then negative, which means west. Then from this point on, I go -15, and that's a little more to scale. And then finally, this is what we're trying to find, the magnitude of our resultant. So, and we'll also need this angle. Okay, -15.016. Actually, you don't need to write the negative in this case because magnitude doesn't care about direction. 56.716. This would be our adjacent because it's touching the angle, and this would be our opposite because it is not touching the angle. So a little bit flipped. That's a thing you gotta learn. Opposite and adjacent are adjacent isn't always gonna be x, and opposite isn't always gonna be y. So our hypotenuse, we would just do 15.016 squared plus 56.716 squared. Square root that, and that gives me, after square rooting, 58.71. So our hypotenuse here is 58.71. So that's answered the first question. Find the resultant displacement's magnitude. We can say the resultant displacement magnitude is equal to 58.71, but that's not our final answer. It wants us to find the direction of the resultant displacement. What it means by that is we also have to find this angle, because this is not perfectly straight horizontally or vertically, so we're going to have to measure the angle there. And the way we can do that is use TOA, or tan equals opposite over adjacent, which in this case we do have, but we're going to use the inverse to find the angle. So tan inverse 15.016 over 56.716. So our angle, which is theta, is equal to approximately 14.8 degrees. And that kind of makes sense as you can see how small the angle is. So 14.8 degrees. Now this is the tricky part. How can you determine what direction this is going? Well, let's look back at our compass. So we can confidently say, and also following judgment of where the hiker was moving, we can say that what is this direction? This is north. What is this direction that is kind of straying off to? This is west. We can say that we're looking at north, and then we stray 14.8 degrees to the west, And so our final answer for find the direction of the resultant displacement, this one kind of already gave us the answer of the direction, but therefore, actually, let me redraw. Okay, so therefore the resultant's magnitude and direction is equal to 58. Well, let's pay attention to significant digits. So it wants us two significant digits. So let's round this to 59. 59 meters. Looking north, straying 14.8, but in this case we'll just do round it to 15. Looking 15 degrees to west, so north 15 degrees west. And that is our final answer. For we found the magnitude, we found the direction. That is how you solve a 2D vector conventions problem with multiple displacements.